my screen. What is, yeah. So for student reporting COVID-19 positive test result, those who are positive, they are saying that they are positive. They should upload their status and details of close contact via my Sejatra, all right? And then follow the procedures set up by the Ministry of Health. That means they should take care of the precautions, test every 3 days, stay at home for for 3 to 5 days, and then Swinburne for the Swinburne complete the Swinburne Health and Declaration form as well. We have the for Swinburne there is a form for health declaration that whether they are close contact or sick or have symptoms or any flu or anything, they should fill it up. And for 7 days quarantine at home, perform lecture and health condition inform lectures or health condition. Yeah, that thank you that you have already informed me. And then attend online classes for 7 days. You should attend the online classes. You shouldn't come to campus for 7 days. So for the student who is tested positive, but for the student who is, where is it? Close contact. Oh, this is, you cannot see, yeah. For the student who is close contact, no, this is not this one, right? Okay, it's better this way. So the student who is tested, I mean, a close contact is this one, that the management procedures by Ministry of Health. So just now, one student sent, I mean, who just shared a file from Ministry of Health, I think, my Sejatra, or what is that? Yeah, here. Che Wenkong, you sent me a file here that you just need to quarantine for a few days. And yeah, for symptomatic 5 days, perform the RTK antigen test and those things. And upload your Sejatra thing. But those who are close contact, for the affected classes attended by COVID-19 positive case, those who are considered close contact or contact, those who were in the class with the same student who is positive now. So Swinburne Health Declaration form, you just need to fill it up that, yeah, you were close contact, you attended the class with a suspected case, and then RTK antigen test, you do it day 1 and day 3. So today and day after tomorrow, that will be on Friday. You just do that antigen test, see whether hopefully everything is fine, it is not positive, and then you can in person attend the class after day 3 if it is okay. Okay, so for asymptomatic and boosted person. So those who are close contact, you don't have to worry much. Hopefully everything is fine. And those who is positive, please stay safe. But I hope that it will be okay for you. You will be recovered soon. Okay, so is it okay now? Is it clear that what we should do? Anybody has any question on this? I will inform my two student, I mean Doris, and also my student Shahira about it. Okay. All right. So since sounds like you don't have any question, now I'm going to the tutorial week 3 and week 4. So we will be discussing about week 3 one first, and then we'll go to the week 4. Right. Oh, hold on. Okay, so here we are for the tutorial 3 and 4, and we'll be discussing about 3 only. The formula for Ki, the following are the examples of 2 groups of compounds. Complete the table by providing the systematic name or a chemical formula for the compounds, either for name or for the formula here. Ki is, I'm not going through all, but some of them are very interesting actually. Potassium iodide, H2O. This is, we all know that is water, right? But is there any other name? Does anybody know that? Is there any other name for this? We have dihydrogen monoxide, yeah? So if we call it dihydrogen monoxide, it sounds like it is very, very chemically. It's a very chemical thing that is just should be in the chemistry lab. But interesting thing is the water that we drink. Magnesium oxide. Magnesium oxide. Magnesium has 2 positive, oxygen oxide has 2 negative. So MnO is just the only thing that we just need to write. So MnO, magnesium oxide. Hydrofluoric acid. Hydrofluoric acid. So HF is simple, but it is also interesting thing that it is acid, right? Since it is acid, it should be in liquid form. We don't need to mention it here when they are standing alone, this formula or the name. But if they are in equation, like in a chemical equation, hydrofluoric acid is being produced from that equation. So we should write in the equation that is L. L means liquid, so that it means it is hydrofluoric acid. It is not a gas. And of course, in the equation, other thing can be produced like X. So it can be aqueous, or it can be gas, or it can be anything solid. Sorry, AQ, not AG. It can be aqueous, or it can be gas, or anything. So when we are showing that, we have to mention it. We have to denote it here that it is L. And hydrofluoric acid means it is a liquid, in liquid form. Barium sulfide. So sulfur is there, so it should be barium. Sulfide is there. Yeah, sorry. So what is the name? MnO. If it is an MnO, what should be it is? What is the name it is for? You're one of the group member, one of the students, they said that whether it will be MnO or MgO. So yeah, I said that it should be MgO. And what is for MnO? Okay, so it should be a manganese oxide. Yeah, thank you. Thank you for who has notified me. Barium sulfide, nitrogen dioxide, ferric nitrate. So it is ferric nitrate means here in this formula, how many iron and how many nitrite actually is there? How many iron and how many nitrate is there? I forgot to turn on my camera, but still when I'm talking, I hope that you know that I'm there, right? Okay, so in this case, where am I? In this case, for ferric nitrite, how many iron atom or ion, or how many nitrite ion are there? So in this case, Fe, it is just one, and then nitrite, 3 nitrite, right? 3 nitrite is attached. So this is one way attaching, this is another nitrite is attaching this side, and there is another nitrite is attaching to other side. Let's say it is here. So in this way, now can anybody tell me what will be the valency for iron, the center? What will be the valence for the iron here, or how many ion? What is the charge that iron is carrying in that particular molecule? Anybody? Is too easy question or? Yes. So Fe3, that means it is ferric. All right. Fe2 would be ferrous, or anyway, Fe3. I mean, the modern nomenclature, we can just call it a iron 3 nitrite, and that will be easier for us. So no need to go in the controversy of ferric and ferrous, or I mean, confusing sometimes this ferric thing, but based on their charges, based on the charge that is carrying, we can just put the name, or put the number iron 3 nitrite. We learned the nomenclature of the chemical compounds in the last class. So depends on there, it is what type of compound it is. Can anybody help me? What type of compound? What are the elements there? I mean, what type of elements are in association to both one another? Anybody? So here we are looking at that one is metal, and then there's another ion which is of course non-metal. What type of bonding it is? Any idea what type of bonding there it should be, or it is there in this molecule or in this compound? better to say. What type of bonding will it be there? One is metal, another ion that is attaching to the metal is non-metal or is gas. It's an ion actually. Ionic bond, yes, that's great. So in if it is an ionic bond, when it is dissolved in water, will it produce a polar or non-polar compound, solution? Will it produce a polar or non-polar solution if it is dissolved in water? Yes, it will produce a polar solution because it is a salt. First of all, it is a salt, so it will be dissolved and it will be easy for it to be dissociated in charge. So it will be 3 positive and then nitrate ion, 3 nitrate ion, of course. Each of them is 1 negative charge. So these 3 nitrate ion attached to this ion. So this way it will be dissociated in water, and that is how there will be the charge separation in the water will produce the compound, the polar solution. The solution will be polar. Carbon tetrafluoride. Carbon is attached to 4-fluorine and it is a carbon tetrafluoride. So what type of bonding it is? Carbon tetrafluoride. Can anybody guess? Carbon tetrafluoride. What type of compound it is? Is it ionic, covalent, polar covalent, metallic bond? What type of bond it is? Any idea? Or if you cannot guess, then any idea why you cannot guess? What type of bonding it is? It is, if we look at the electronegativity difference between carbon and fluorine, we'll say that it is quite close. I mean, not like sodium and fluorine. So carbon, then nitrogen, then oxygen, then fluorine. So they are quite close. And that is why the electronegativity difference is not more than 2. So it is a covalent bond. They are in covalent bond. Which group of compound are ionic compound and which group are covalent compound? How can you tell? Okay, so group 1 or group 2, I already have discussed actually a bit. So how many of us are for group 1 to be covalent? Group 1 to be covalent. How many of you agree? How many do you agree for group 2 to be covalent? I just have already just mentioned it or discussed that group 2 here is the covalent bond because you see that nitrogen, oxygen, hydrogen, fluorine, ammonia is NH3. So their electronegativity difference is not that high, and that would be group 2. So all of them is covalent, and here it is ionic compound. As we go up or down, doesn't matter. This group will be ionic compound. Can anybody give me just one? Just one reason. There can be many reasons, but just one reason why group 1 should be ionic compound. Varun, yes? Yes, good. Metal and non-metal. Very good. Quick answer. Yes, thinking. So there is all we see. All we see is metal. Potassium is metal. Manganese is magnesium should be. Yeah, Mg. Magnesium, barium, iron, nickel, carbonate, nickel 2 carbonate. So yeah, this is important thing that I should have written before. Nickel 2 carbonate. So let me write nickel carbonate, CO3. CO3 is carbonate. And then what? I put 2, right? Just like iron nitride. So nickel 2 carbonate. So here is as well, this is nickel is metal. So metal and non-metal are there. So they are chemical, ionic compounds. The orbital, the shapes and everything that we have a better understanding about the shape and size and the electron filling up the orbital and why some of them are giving different type of different valencies. Can I ask one quick question? Yeah, Veron, you have, okay, how do I? Okay, anybody has any questions so far? Veron, yeah, once again. Any other question? Okay. If there were a question, just let me know if you have a question. Anyone has a question. My question I wanted to ask that yeah, I remember that alkali metal or alkali earth metal, they have their valences is very fixed, like sodium, potassium, cesium, rubidium, all of them has lithium. They have only one valences, that is +1. That is +1. If I want to show you the periodic table, then it will be easier. Yeah, so this is the periodic table. So lithium, sodium, potassium, rubidium, cesium, all of them has one positive charge, or they can form only one valences. Beryllium, magnesium, calcium, strontium, barium, and radium. Although radium is different, but all of them has 2 positive charge. Whereas chromium, cobalt, nickel, copper, zinc, molybdenum, titanium, ruthenium, whatever, silver, cadmium, they have more than one charge. Why it is so? What is the reason behind it? Can anybody tell me what is the reason behind it? Just I want to, let's discuss. That would be good if we have a discussion. What is the difference, or why it is so that they do not have, they have only 1 or 2, but here they have many? Can anybody give me an answer for this? Or anybody wants to try to give an answer? No? Because they have to, this has to do with some kind of electron availability and electron distribution in their atoms, electron distribution. And the electron, the filling up of the electron, the procedure to fill up the electron into that, into the orbitals of that respective atom. So for metal, once again, they have d orbitals, and then in d orbital, their d orbital can house 10 electrons. 10 electrons, very long, very big, right? I mean, quite much, 10 electrons. And that is why they can go here and there, and they have variable 10 valences. That is why, because electrons can go into these d orbitals. But for alkali metal, alkali earth metal, that is lithium, sodium, potassium, or barium, magnesium, calcium, this group, they do not have these d orbitals, so electron cannot jump from and cannot go and hide into that big electron cloud. They are very precise, they are very restricted, so only s orbital or maximum p orbital they have. Okay, so this is the one thing, and now we are moving to the same. Okay, here. Why is the energy lower than the other? Sodium and chloride. So here it is a sodium and it's a chlorine gas, but they are atomic in consideration. So sodium is a monoatomic, no problem. So first ionization energy is positive 394 kilojoule. Okay, first ionization energy is 494 kilojoule. And chlorine, to become chloride, electron affinity is negative 349. That means 150, almost 150 times, I mean, kilojoule less than that first ionization energy of sodium. So positive and negative charges ion attract each other electrostatically, and the attractive force is called ionic bonding. The bonding, the Coulomb's law, this is the Coulomb's law that tells us the strength of the bond that will be formed between positive and negative charges. For one positive and negative charge, for sodium and chloride per se, that we can find out this F K is the constant and is electrostatic energy, right? Is constant, is values, and this is 2.31 times 10 negative 19 joule nanometer. So given on this fact, or using this equation, we can find out the strength or estimate the bond energy of sodium chloride in the bond, sodium chloride bond energy for one molecule. So the distance between sodium and chloride ion, these two ions that we have seen before, is it here? The sodium and chloride ion is, sodium is but smaller because it has 10, chlorine is a bit bigger. So here is chloride and sodium, and then this the bond distance between them is 2.276 nanometer, right? 276 nanometer when there is a bond formation already. That means they come close enough, they are touching each other. So the distance between two nucleus, the two nucleus is 0.276, right? So this is the distance between them. Estimate the bond energy of sodium chloride in joule per ion pair. then convert the value to kilojoule per mole. So first of all, what will be the energy? What will be the energy between them? Sodium chloride ion. We can find out from here. It's quite easy. We have this value 2.31 times 10 negative 19 joule nanometer, and it is Q plus Q times Q negative, positive and negative charge. So it will be, both of them are 1. Both of them are 1. So plus 1 minus 1 times it should be negative 1. And distance between them is 0.276, right? The distance is 0.276. If the distance is bigger or wider, longer, or long distance, so the whole value will be divided by a bigger value here. If the distance is big, it will be divided by a bigger figure, so that the whole result will be less, reduced, which is I'm going to talk later on. So in this case, we see that 2.31 times 10 negative 19 joule nanometer, and it is 1 negative 1, so it will be negative 1, and it is 0.276 nanometer, so it will be divided by 0.276 nanometer. So altogether, everything included, then we will get the nanometer cancelled out only in joule. So 1000 joule is 1 kilojoule. In that way, I will convert this joule, the amount that I will get, to joule. All right. So it is quite difficult to write here, and 2.31 times 10 negative 19 times 1 plus 1 and negative 1. Okay, I'm just doing it as it is written on the book, divided by 0.276, and it will be in joule. So we have to divide by 1000. 1 kilojoule means 1000 joule. 1000 joule, right? 1000 joule. And then also, first we have converted to joule, but then we have to convert it to moles. This is per pair. This is one pair. This whole in energy was for one pair. So in one pair, sorry, in 1 mole, how many pairs will be there? Any idea how many pairs will be in 1 mole? Avogadro's number, of course. So we will have Avogadro's number of ion pair. What is it? Avogadro's number of ion pair in 1 mole. So times Avogadro's number of 0. What is the Avogadro's number? Yeah, I forgotten. What is the Avogadro's number? Anybody? 6.023 times 10 negative 23rd, right? So we have to multiply 6.023 times 10 power 1023rd number of ion pairs by 1 mole. So it will be in that way we can find out what is the total energy for 1 mole of sodium and chloride. Second question says that, do you expect sodium bromide to have a higher bond energy than sodium chloride? What is your guess? It is a menti question for you guys. What do you think that will sodium bromide will have a higher bond energy than sodium chloride? That means the bond energy will be higher, or the is a bigger figure or is a lower figure? It's a menti question for you. I will just yes or no should be okay. So I'll take 5 minutes break, and in that 5 minutes, please let me know what do you think, whether it will be higher or lower, the bond energy for sodium bromide. No, I'm not talking. I say that I'm taking 5 minutes break for you guys to give, for you to do or come up with your idea or your answer so that then I will discuss. Oh, yeah, now I'm here back. So, what is the answer for that? Metal and non is higher. Yes, I mean sodium chloride is higher. Gabriel says, I mean sodium chloride is higher. Yes, higher. So, Gabriel is a bit ambiguous. You are saying that sodium chloride is higher, or you are asking me whether sodium chloride is higher or not? Is And Ainin, you didn't give me an answer. Audrey, you also didn't give me any answer. So the answer for this sodium and bromide, which is bigger molecule, chlorine or bromine? Sodium is sodium, both are sodium. So chlorine or bromine, which is bigger? Let's go by logic. Sodium or bromine? Sorry, chloride or bromide, which is bromine is bigger, yes. Yeah, bromine is bigger. So the distance between sodium and bromine will be longer, will be bigger. The distance is longer between sodium and bromide. So in that case, the D is going to increase. So sodium for sodium bromide, right? So if the D is increased, the whole value divided by a bigger value, it will be reduced. So energy for sodium bromide is less than the sodium chloride. And that is why sodium bromide is easy to be broken, to be dissociated. Or by the same logic, if you go down this periodic table, iodine will be even bigger, the molecule, and it is even easier to break. The iodine is to dissociate in water, right? The bond is easier to break. So that is why hydroiodic acid is much stronger acid than hydrobromic hydrofluoric, hydrochloric, and all those things. Because it is easy for hydroiodide to release the hydrogen from its cell. All right, so physical properties of ionic compound, of course, the high melting point, do not conduct electricity, soluble in water. When they are solid form, they do not conduct electricity, but when they are molten or soluble, they are very much conductive of electricity. So, yeah, now bond energy. Now the thing is a high melting point that we say that those who are ionic bond, they have high melting point. But do you know what is the highest energy? What is the highest energy needed for a bond to be broken? What is the strongest material? Do you know what is that? What is the strongest material in the world? That is diamond. And diamond, interestingly, it is carbon and hydrogen. And yes, Eileen got it right. And yeah, diamond. So what type of bonding is in diamond, Eileen? Any idea? Carbon and hydrogen, right? In diamond was hydrogen, carbon and carbon, not carbon, hydrogen. Carbon, diamond is a carbon. This is another the very refined or depressed pressurized look of graphite. Graphite is black. Diamond is what? Diamond is diamond, and everybody likes diamond because diamond has gone through a very high heat and pressure and distress, so it becomes diamond. So that is why that diamond is a very strong material. And interesting is it is carbon and carbon. That means it is a covalent bonding between them. Interesting, right? Okay. Have you heard that graphene? Have you heard of graphene? Anybody had heard graphene? What is graphene? No. Graphene is another strongest material, like 5 to 7 times more stronger than steel, but it is 20 times less weight, less heavier than steel. So now a lot of research is going on to produce graphene, and in a bigger scale to produce the high strong materials like aircraft or military grade materials. So graphene as well is just carbon. It's a special arrangement of carbon attached together to form a network, and that is why it's called the graphene network. And it is one of the strongest material now in the world, and so small, so thin material. So there as well it is. Excuse me. So it is as well just carbon and carbon. So it's not necessarily that high melting is always can be associated with the ionic bonding. There are something that their structure, all right, there's how they are arranged or organized in a lattice. So what is lattice? What is crystalline? We structure of all those things. These things are coming up, so we need to discuss a little bit more. Lattice energy is what that energy for one material. They are in a group, or they are bonded together in a certain way, in a what do you call it, to break it from solid to liquid form. So that is called lattice energy. I mean, lattice. They are arranged in a three-dimensional figure, three-dimensional way, so that it looks like a crystallic form. So to break that one is called the lattice energy. And another thing that we just got, crystalline structure. So if it is crystal, means they have plane and they have cone size in their structure, and in a regular pattern of that structure, so that solid will be in a regular fashion. So all of them, all the small chunks of the material, if we dissect or we can break, if we break, we will find a pattern in their structure, physical structure, in their physical structure. So it will be crystalline structure, we call it. Okay. And the following is the table showing the data related to ionic compound. Sodium fluoride, the melting point is 1012 degrees centigrade, whereas calcium oxide is 2580, right? And sodium chloride, sodium bromide, sodium iodide, all it is are reducing from up point up to here. This is not in the same group, so we will talk it with a bit later. But from here we see these all fluorine, chlorine, bromine, iodine. These are from the same group, and they are going down the same group. We see that the size of the molecule or ion is increasing, and that is why their distance is increasing, and their melting point is reducing, so their bond energy is less or weaker. And sodium fluoride, of course, fluorine is very electronegative. They do not want to break, they do not want to give up the electron and go back to original fluoride, and that is why you need to have more energy to put. But what happened to the calcium oxide? Why calcium oxide is much higher than sodium fluoride even, right? What is the purpose of it? Anybody can have a little bit what do you call it, idea of why sodium fluoride is calcium oxide is much stronger. Any idea? Or anybody wants to chip in? Sodium fluoride, calcium oxide, why will it be higher energy? No? I need typing. I'll be waiting for her to. Calcium oxide. Calcium, what is the valence for calcium, or the maximum ion they can form is 2 positive. Oxygen also 2 negative. So they have the charge density of 2 electrons, just double of sodium chloride or sodium fluoride or sodium iodide, right? So calcium has 2 positive and 2 negative. So their bond is much stronger than 1 to 1. And that is why their energy is much higher to break. Okay. So the outline the general relationship between lattice energy and melting point. The higher the lattice energy, the melting point will go high as well, right? And that is why the higher the lattice energy, sorry, I was reading an email. Now, okay, lattice energy and melting point. So higher the lattice energy, the melting point will be higher as well. Because in one lattice, that means, let's say I am drawing a crystal structure. I'm drawing a crystal structure. We know this is a crystal. This way, let's say we remember this way, the crystal, no, it's quite, okay. Let's say this is crystal. They are forming crystals in this way. And if the crystal is in this stable or in a regular form, so you have to break it first. The crystal has to be broken first and then separated, and only then they will get to start melting, right? So that is why if the crystals are strong, the crystals, lattice energy is strong, the melting point will be stronger as well. Higher as well. Calcium oxide has a much higher melting point because calcium and oxygen, it is 2 positive calcium and oxygen is 2 negative. So the bond between them is two bonds they are forming between them. So that is why to break 2 bonds, it is always you will need more energy for them to break. The graph above shows the changes in potential energy of 2 atom system as distance between nuclei. So what does it mean? The green circle, or for now I make it red, what does it mean? It means that this is the lowest energy, lowest potential energy. And that is why they are more stable. Whatever molecule they are here, coming X or Y, calcium or oxide, sodium and whatever it is, they are at this moment, at this point, the distance is around, what will be the distance? 5.5, maybe, or 6. Let's say 6 nanometer. For the convenience, we just consider 6 nanometer. So at 6 nanometer, when their distance is 6 nanometer from one nucleus to another nucleus, so they will have the lowest energy, which is around negative 200 kilojoule per mole. So they will be stronger here. They will be much stable here. According to the graph, what is the approximate average bond length of the system of atom? What is the approximate bond distance between the system of atoms? There is one trick here. System of atoms, right? System of atom. From here, there is impossible to tell which atom, let's say there are 2 atoms here. So which atom has what distance or what radius? It's impossible to tell. But when we call the system of atoms, what does it mean? The system of atoms is the atoms are in association, right? The atoms are in association and they form a system between themselves. So that means it is a molecule. And if it is a molecule, the distance between them is around 5.5 or 6, or if somebody say no, it's 5, so okay, it's fine, because it is not graduated, so the margin of error is quite big, isn't it? If it's 10 is here, 11 is here, 12 is here, 13, 14, 15, I cannot even make it even or precisely 10 section 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh no, yeah. But anyway, if anybody says 5 or even says 6, it is okay since it is not graduated. So the distance between the system of atoms, that means molecule, is around 5 to 6 nanometer. If the atoms in the graph were at their most stable bond for length, how much energy would be needed to separate 1 mole of atom pairs completely? 1 mole of atom pair completely. So far, you can consider that we are talking about 1 atom, right? 1 atom we are considering, not like this, X and Y. You can say that XY atom, molecule, sorry, XY molecule we are talking so far. But here the potential energy is per mole, is saying. So our endeavor or our try is much easier now. Our task is much easier now. So kilojoule per mole, it says that. Where just now I saw per mole, 1 mole of atoms pair completely needed. Of course, we need 200 to go up in there, so that the distance will be this far, and then it will be no bond anymore between them. And also to release to form 1 mole of bonded atom pair, just no bond, molecule, but just atoms, just pair of atoms. Yeah. So we need 200 kilojoule of energy to provide them with, so that they will far away. When we provide energy, what will happen? They will start to fight. They will be energetic. They will start to react with that energy, with given energy, and they will not be bonded anymore. They will go far away. They will be associated one nearby, but no bonding anymore. So 200 and 200 here both. Explain in terms in the attractive and repulsive force what happens when the atoms are more than 15 nanometer, less than 5 nanometer apart. More than 15 nanometer, that means here already there is no bond anymore. It's broken. It is potential energy is 0. There is no potential energy at all, right? So they are stable. They are staying together. Separately, but they are not doing the reaction. They're going to disturb anyone else. When they have more positive energy, they will go to disturb. Disturb means in this case that for your convenience, I'm telling disturb, but disturb means they are going to react. They will be reacting. But if no, 0, that means they are stable. They will stay as itself by themselves separately. So by when it's 15, and when it's less than 6 or 5, here or here, what will happen is their repulsive energy will be too high that it will go up to that positive side, and then they will repel each other. So there will be no bond as well, less than 5 nanometer apart. The following is a table comparing the average bond length and average bond energy of 3 halogens: chlorine, bromine, iodine. Average bond length 199, 288, 267, and average bond energy kilojoule per mole. Of course, when it is going, the bond length is going higher, it is reducing, the energy is being reduced. Average bond length vary. Why the average bond length vary with the 3 halogens? Why does it vary? Because of their size. And with the increase of size, what increases? Or in other way, Why does the size increases? It's another last question. Okay, last Menti question for you. Why does the energy reduce? The size increases from fluorine to iodine? As we see in the periodic table, their size is increasing. Why? Just answer. It doesn't matter if it is a very simple question or a very stupid question. Don't bother. Just answer your. Give me your answer. What do you think? That why should it be bigger in size? What makes them bigger to grow in size? Baron shells, good. The electron shells, good. The reason I didn't put it in a Menti question because yeah, somebody else was typing. Cheo and Con, I saw you typing. Why did you stop? Jonathan, are you there? Okay. Answer came out, but I still want to see your answer. Jonathan, Chen, Liantio, Gabriel, Keshwan, are you guys there? Okay. Good, but why? All right, good that you are here. I was expecting some answer from every of you to participate. Why? Baron. Okay, so why are the size increases? There are possible three question. Answer came out: the shells, electron shells, and from Chem and Con, the shells. The answer came out already. So the thing is, electron is coming late, but first their proton number, the nucleus is heavier. The nucleus is heavier, and that is why to counter that nuclear charge, the electrons are being filled up. Okay, so that is why their size is increasing. And the question was here, why the average bond length? Yeah, because of their size, the bond length is increasing as well. And it is the longer the bond length, the lesser the energy, the energy getting less if the bond is higher, longer. Predict which halogen is the most chemical reactive, thermally most stable halogen. Okay. One question is easy, another question is takes a bit of thinking. Both are easy. So I want to hear from you the easy one. Which one of them is easy to break? The most chemical, the most chemical reactive halogen. Which of them will be most reactive among these 3 or 4? What do you think that which one is most reactive? Come on. Just type. It's so easy. You don't need to put the formula, just HF or HCl or HI, something like that. It's so easy. What do you think? Ainin, you have been quiet for some time. Cheo and Kong say chlorine. Jonathan say chlorine. Yeah, just give your answer. What do you think? Which one will be most reactive among them? The most reactive chemical, most chemical reactive halogen. Fluorine, chlorine, fluorine, chlorine. Yeah, good, good, good. So many possible answer came out. Anybody else want to chip in? Chlorine, 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 fluorine. Here, iodine, chlorine, chlorine, chlorine. Okay, most of us has voted for chlorine, but once again, you see that here as we go down, iodine is bigger, the bond average bond energy is less, so of course it is easy to break. Chlorine needs 243. Chlorine is 243 to break. Iodine is only like 100 kilojoule less than that of chlorine. So it is, of course, it is higher. Iodine, it will be much reactive. So it will be easily broken. And once it is broken, what will it form? If it is broken, iodine or chlorine or fluorine, whatever, if it is broken, what will it form? It will form iodine ion, right? Iodine ion, like this. Iodine and another iodine. So there are two iodine negative form, and since they are negatively charged, so they'll be reactive. When they are in association producing iodine molecule, they are neutral, but when they are iodine ion, they will be negative ion, and then they will be more active. For chlorine as well, they will form the chloride ion. Sorry, this is iodide ion. So this is chloride ion, but it takes 243, 250 kilojoule on around 250 kilojoules. So it is much stronger, higher energy you need, just because their bond energy is less. And oh, fluorine, somebody or some of you say fluorine. Fluorine even not in the chart. Fluorine is a little bit different. Chemistry all about exception. So fluorine is a little bit difficult to deal with because it is so electronegative. I think there was a table just now somewhere. We just saw it. Yeah. So fluorine, sodium fluoride is 1012. So fluorine and fluorine, if there are, it is much higher, and it is very hard to get the fluorine dissociated to produce fluoride ion. So yeah, so this is not in the chart. Which will be the thermally most stable halogen? Thermally stable halogen. All right. So when thermally stable halogen, yesterday we have done the decomposition reaction. Have you done decomposition reaction yesterday? How many of you have tested the decomposition reaction yesterday? We have done decomposition, right? Yes. Okay, we have done the decomposition reaction yesterday, and then what did you do? Yes, thermal decomposition, yes. Thermal decomposition. Yeah, sorry, I should mention thermal. So that the decomposition happened in presence of heat. So in that decomposition reaction, we use lead nitrate and put it on heat so that we saw a gas is coming out from the tube, and that gas glows in the dark. The gas helps the fire to glow, and also it is turn the litmus paper to reddish. So my question is, what is decomposition actually? It was in the manual yesterday. So decomposition in presence, it is not like melting. It is not melting. The lead nitrate yesterday, it was not melting. You saw it that at the bottom there are still some solid, although it changes color, but still solid. It was not liquid, or it did not change its physical state. It changes its appearance, but still there was something coming out of it. So decomposition is, it is breaking down. All right, it is breaking down to different type of elements it has within it itself, and that is the decomposition reaction. So in presence of heat, it can be decomposed. In presence of light, it can be decomposed. And for the thermally most stable halogen, that here we are saying the thermally most stable halogen should be chlorine gas, because it has higher temperature, energy to break. It needs more energy or more heat. In that way, energy means heat to break it and make it separate. Comparing to the melting and boiling, chlorine has the lowest boiling point and melting point compared to the other halogens. This is because it is a non-polar molecule and experiences the weak van der Waals force between molecules. Okay, so the melting temperature and boiling temperature, if we compare, the chlorine will be lowest because it has shorter bond, and they are in covalent bonding between them, so they will have lowest boiling point. All right, smaller molecules, so they have lowest boiling point and melting points compared to other halogens as well, because it is what do you call it, small bonding, so that, and covalent bonding, so the charge separation between them is less. So let's say this 2-chlorine, this 2-chlorine is here, and then the electrons, let's say this electron they are sharing, should be here actually, the 2 electrons they are sharing. Since there is a smaller size, the electrons are close to each other, so they do not have the charge separation. But for iodine, let's say this is, I should make it bigger. Iodine is bigger molecule, right? And they have 2 electrons here, iodine. So because of their bigger size, they will have a charge separation, positive, delta positive and delta negative. Why it is so? Because when it is, the electrons is moving, at some part the electrons can be here. 2 electrons can be on one atom, and since it's bigger, it's taking time to come to a common place, and that moment is a fraction of a, what do you say, that nanosecond. Probably it is negative charge, it is positive, and vice versa. So that is why it is a bit more easier to become separated or ionic form for bigger molecules. Anyway, so thermally most stable halogen should be chlorine. So it is easier to break, hard to break. Electronegativity and the periodic table. Electronegativity, we have talked quite some time for it. So if we are going from left bottom corner to right top corner, it will be the electronegativity is increasing, and from left bottom to up, the electronegativity is also increasing for the elements on that. And the electronegativity difference, if the electronegativity difference is more than 1.7, right, then the bond energy is more or less 50% ionic. If it is less than 1.7, the bond energy should be, by definition, is covalent type bonding. And so what type of bondings are here? We need to find out the difference. Hydrogen and fluorine. Hydrogen has a electronegativity 2.1, fluorine has 4. So the difference is 1.9 and it is more than 1.7. So the bond is more or less 50% ionic. But if it is more than 2, so we can consider, or you can call it that, okay, it is completely ionic bonding. But hydrogen and fluorine, it is polar covalent bond. We can say it's polar covalent bond because it is not totally ionic. It's it is not covalent, but it is towards the ionic side, and that is why we can call sodium, chlorine. Doesn't matter how many chlorines are here. We just need to consider one electronegativity at a time. So sodium. Nitrogen, sorry, it is not sodium, right? Nitrogen trichloride. So nitrogen is 3 and chlorine is also 3. So 3 minus 3 is 0. So it will be covalent bond. And this is how we can find out all the bond nature of the bonds, whether it will be covalent or not covalent, pure ionic or whatever. So if it is more than 2, it will be ionic bonding, right? And for this one, these all things are for you to try and find out what will be the bonding types between them. Non-polar diatomic molecule. This is what I was talking, that when it is a diatomic but non-polar, purely covalent, then the electron density is, or electron is always, wherever you consider it, right? It is here or it is there, wherever you consider the electron is almost equal distance to both of the atoms. It's atom A, it is atom B. All right, all the same element, let's say it's chlorine and chlorine. So all the electrons around it is at the same distance, a similar distance between them. But when is a polar bonding, the electron density, sometimes it is here, and then this B is being deprived of these electrons, and sometimes it is here. So this electron, A will be deprived of that electron. So electron charge, electron will be different. Electron sharing will be different between them too. And that's how they will be formed, the polar bonding. Question 9 says that describe the two types of bond of chlorine gas and hydrogen chloride gas. Hydrogen chloride, when we say, that means we are saying that we are referring to gas. But if we say hydrochloric, that means we are referring to HCl acid. So chloride, hyd is gas, ic is acid, or in liquid form, ic in liquid form. Use your understanding on the nature of the bond, predict which gas is not responsive to an electric field with opposite charge plate and why. So is in an electric field with opposite charge plate, let's say that this is two charge plate and they are connected to a battery, positive and negative. Let's say it's positive, is negative, charged to a battery, right? And there is HCl gas in this chamber. It's a chamber, and there are chlorine gas as well. So which of them will react, or which of them will respond to this different type, in between these two type of different charges, charge plate. Since chlorine is non-polar molecule, chlorine gas, diatomic Cl2 is non-polar because their electronegativity difference is 0. So that means it's purely covalent. We can consider now that it's purely covalent. And the charge is also evenly distributed on both of the atoms. So, and throughout this molecule. So this will make it a neutral and will not be attracted to either of the plates. So it will not go to positive side or negative side. But for HCl, the HCl is already polar covalent, right? So we know that the charge difference is hydrogen is positively slightly positive charge, chloride is slightly negative charge. So that is how it will the hydrogen will go to a negative plate. Let's say that it is a negative plate. It is a negative plate and is a positive plate. So hydrogen will be attached to this side. Hydrogen will be attached to this side and chloride will be attached to this side if in HCl. And now you are smart enough to understand that how hydrogen can be produced from a molecule where hydrogen is there, or a polar covalent bond, or from H2O also, how hydrogen could be produced. But the thing is, it needs a lot of energy, then a lot of electricity, and that is why it is very much cost intensive. It is very much expensive to produce this way. And that is why there are a lot of research is going on. So what type of catalyst we can use or how we can make it energy efficient, so that to some extent people are coming up with the idea that we don't need any energy, we don't need any electricity, we just put some membrane type of things or some catalyst where this HCl will sit on the catalyst, right? And then they will be separated in hydrogen and chloride gas. Hydrogen will come out from one end, chlorine will come out from another end. And since you are already half of the engineers, chemical engineers, probably you can think about it later on when you go up to the FYP or do your research later on. For question number B, it says which gas is soluble in water? Chlorine, once again, gas is non-polar, right? So they will not be soluble, but HCl, it will be soluble in water. Okay, so compare the following table: type of bonding, polarity, instant coffee. Instant coffee, it readily dissolves in water, right? So the polarity is supposed to be high. Otherwise, why it should be dissolved in water? Peanut butter, it does not dissolve in water. Sorry, it does not dissolve in based on two different water or terpene. Okay, so peanut butter in turpentine or terpene, it will not be dissolved in terpene. Terpene is the organic solvent, and peanut butter will not be dissolved in this organic solvent, so that it will be in that solvent, it is not polar. And sunblock lotion is also in terpene, it will not be dissolved, so it is not polar. And mostly when you develop a sunblock lotion, make sure that it does not get dissolved in water as well, not that easily. Okay, if it is easily dissolved in water, so people are going to the sea, to the beach, and there they apply the sunblock on their body and go into the water, come up, the sunblock gone. Or if it is not totally soluble, then what will happen? You put it on your skin, you cannot remove it. You need something else to remove that thing, right? So based on their the usage, you engineers need to be very prudent. You have to think what the uses of this product and how can you make it better for people or customer to use it, to buy it. Solute, bonding type, polarity, and suitable solvent. Tell salt, sodium chloride. So what type of bonding it is?
ionic bond, of course, we know it. And sodium chloride, since it is a salt, the polarity should be high. And suitable solvent is any polar solvent, basically any polar solvent. But if it wants us to know that what will be the soluble solvent, suitable solvent, it will be water, right? And sugar, it is dissolved in water as well, and then table sugar actually. So it is polar and suitable solvent is water, but still table salt, since carbon, hydrogen, and oxygen together, they are the polar covalent. It is not ionic, but polar, this is ionic. This is not ionic, it's polar covalent. Vegetable oil is covalent bonding. There is interesting thing actually. This part is covalently bond. This is what do you call it? Polar covalent. So there are two parts actually, and because of this, vegetable oil, it can be dissolved. This part can be attracted to polar solution, but this part does not get dissolved in water. And that is why the soap is produced in this way. So soap also has this type of, not acid, but this there is a salt will be added to that acid. So that salt part is much more soluble. It is much more ionic. If there is a salt, it will be much more ionic. And since it will be ionic, this ionic part will be dissolved in water. And this non-ionic part, which is CnH2ICN+1, what does it mean? We will learn more about it in organic chemistry. So this part will be dissolved in not polar, means in oil or fats or organic solvent, but this part will be dissolved in water. So two parts are dissolved in two different things, two different type of solvent. What is happening in this case? For soap, soaps are made from vegetable oils, right? So in this case, it will be pulled apart. It will pull apart, or it will pull the dirt apart from your clothing, and that is how actually it clean the dirt from or remove the stain from our clothing. So all these things you can go around. And the loose structure, we will be discussing about it in the next lecture class first, and then we'll move to this. But the loose structure will be included in your test. The test one coming next week, the Tuesday, our regular lab session. Since next week there will be no lab, we'll be using that space and time to conduct our first test. So the test next week will include everything until today, or sorry, until the next class, until next Thursday, and until the Lewis structure will be also included in that test. So yeah, this is it for today. Anyone has any question? Do you have any question? Anyone? Okay, thank you, Audrey, for your reply. Anybody has any question? All right, thank you for your reply. So I'll be seeing you on Thursday. Please do take care. Do the testing on you today and day after tomorrow, and stay for these 2-3 days. The student who was tested positive, please stay at home for these 3 days and take care. And I hope that you will be cured soon. Okay, so I'll stop recording now and I'll see you on Thursday.